Hi, my name is Diana Jaramillo, and this is my extra credit submission. Okay, so the first problem involves the two treatment conditions are being compared. So it's an independent measures research study, and so this is how we complete it. So we have the first step, which is the hypothesis. And the null hypothesis indicates that there's no difference between the population means, so population 1 equals population 2. Or you could also write population 1 minus population 2 equals 0. And the alternative hypothesis is that there is a difference in the mean population. So you say that mean 1 minus mean 2 does not equal 0. For our next step, it's to find the critical regions. And so to do that, you need to find the degrees of freedom. And to find the degrees of freedom for a two treatment condition or an independent measures research, you need to do either degrees of freedom 1 plus degrees of freedom 2, or n1 minus 1 plus n2 minus 1. And so that will give you 14. And then here are just the sample size for sample 1 or reinforcement schedule A, which is 8, and the sample size for reinforcement schedule B, which is 8 as well. And these are the means for those two data sets as well. So now we find out what the critical regions are, and this particular question is a two-tailed t-test with the alpha level of 0.05. So if we look at the table, then, and if we look at the t-distribution graph for a two-tail at 0.05 with degrees of freedom of 14, like we found before, that is 2.145. So that's what we got here as well. And that is positive or negative 2.145 because it is a two-tailed. So we don't know which direction it's going in. And for our next step, we compute the t-statistics, which first we need to do the sum of squares. So we have to square the x values. We have to sum up the x values as well as the y. So sample 1 and sample 2. And for the first sample, we have sum of x, which is 51. So when we add up all those numbers, it gives us 51. And if we square those x's and add them up, then we get 339, and it's an n of 8. So if we plug it into the formula, it'll give us 13.875. And then for the second sample, the sum of x is 43, and when we square the x's and add them together, we get 251 with an n of 8. And when we plug it into the formula, it gives us 19.875. And then, since this is, again, an independent measures research study, we have to find a pool variance instead of normal variance because it involves two different treatments that are being compared. So when we plug it, this is a formula. SS1 plus SS2 over degrees of freedom 1 plus degrees of freedom 2. So we get these numbers from our sum of squares, of sample 1 and sample 2 and the degrees of freedom, and that gives us a pooled variance of 2.4107. And then we use that pooled variance to find the estimated standard error. And so the formula for the estimated standard error is the square root of pool variance over n1 plus pool variance over n2. So if we plug that in to the formula, and we're 8, they give us 0.776 for the estimated standard error. And then we find t, which in this case is mean 1 minus mean 2 of the sample and the population means, but population means in this case is 0, so we cross that out over standard error. So like I figured out before, the mean for sample 1 was 6.37, the mean for sample 2 was 5.375. So we plug that in for the formula over the standard error, and that gives us 1.288. Now we can make a decision, since again the critical T region, which we found in step 2, was plus or minus 2.145, and our T calculated was 1.288. It does not fall in the critical T region, so we conclude that the evidence in the data shows that there is no significance in the two different positive reinforcement schedules that Bernie gives to the pigeons. T of degrees of freedom 14 equals 1.288, and so P is greater than 0.05. So therefore we failed to reject the null hypothesis, and which was that population 1 minus population 2 equals 0, so that there was no significance. Yep, and that's it for the first short answer question.